Okey-dokey. So my name is Paton, right here. I'm currently a sophomore at VTC here, and my project here is the Sun Charger 2410, which is a solar charge controller, right? And the purpose of this is to control the charging of the batteries. It's quite important. You want to prevent the overcharge, prevent overcharging the batteries, which helps extend the battery life. And also control the load. In my particular charge controller here, these are the things that my controller will be doing. So number two, control the load, which is basically when it recognizes that the battery voltage drops below a certain percentage, say like 80%, which corresponds to about 11 volts or so, it will disconnect the load there. Monitor the power, so it'll tell you like the voltage at the battery and the solar, and the current that the load is drawing and the current that's coming from the solar panel. Also blocks reverse current so that the battery can't charge back into the solar panel. And there are fuses installed, which is the overload protection. So if you happen to blow a fuse, you can easily replace that. In the title, the Sun Charger 2410, the 2410 pretty much stands for the parameters, which is a 12 or 24 volt nominal solar array input with a max of 10 amps. So you can connect the solar panels in parallel to, if you got smaller solar panels like 100 watts that may only be 5 amps a piece or something like that, you could connect two of them in parallel. No more than 10 amps input. 12 volt battery bank, this is what this is, my controller is designed and optimized for. And 10 amps output, although that can be changed. My board allows for definitely higher. You could even put a 20 amp fuse in there and draw 20 amps off the battery. So, kind of visual representation here from the solar panel coming down, right? We have pretty much like the heart of the board, the buck converter, and that comes over, that gets connected to the battery here. Off the battery, we have the 5 volt regulator, which supplies the microboard and sensors and anything else with the 5 volts that's required to operate. And let me back up here. So from the solar panel here, we have the voltage sensor and current sensor that's being detected there from the solar panel before going to the bus converter. Coming back here to the battery here, also goes to this load on off, which is basically a simple switch. Getting the low voltage disconnect tells it, okay, it's too low, so it disconnects it from the load here, and which also has a current sensor coming from that, which is being fed back to the microboard, so it displays on the LCD screen up there, and there's also LED indicators coming from my microboard. And and importantly, the microboard is determining, based on the voltage at the battery, what to do with the buck converter by sending it PWM signals. So, classic buck configuration here, circuit. See, it's basically switch closes, right? Charges up the inductor, builds voltage across the inductor, plus minus. Switch opens, switches polarity. This now acts as a forward conducts. It's acting as a switch as well, and it pumps the charge into the load here, which is my battery, and the VN would be my solar panel. So this is my switching circuit. I have a P-channel MOSFET up here that's actually rated for 27 amps. So I could probably, down the road, up that 10 amp input, which needs a negative voltage at the gate to turn it on, and that's why I have this voltage divider here. And so when this coming from my microboard here is well, it's a constant frequency, and it sends the signal to turn it on and off. And when that gets turned on, it gets pulled down to ground, and there's a voltage divider there, so it not to go past the gate to source voltage, which is like negative 25. So that's why that voltage divider is there. And that's pretty good there. And this is stuff that I used to calculate what I needed for resistor values over there, formulas. Yeah, so choosing the inductor here, basically this one here, I had a 15 microhenry toroidal inductor, and operating at 15 kilohertz. This was with, I think, 50% duty cycle. This was operating in discontinuous mode, which basically, in common practice, I don't think is what's desired, but as far as what I'm reading online and stuff, but this basically what it means is that the current in the inductor here, the blue waveform, is falling basically to zero. So this was before the inductor, the green is after the inductor, and well, I had a sampling resistor in there. And the current is building up when the yellow is high, which is when that MOSFET's on, current's building up, and then it's discharging when the MOSFET's off, and it's falling to zero. I think quicker than I would have liked it to, so that's why I changed the inductor, which I'll probably end up changing again because I still don't like it. But it's an 80 microhenry now, operating at 15 kilohertz still. But we can see here, basically ignore the purple waveform. This is just the math function here. With this MOSFET yellow waveform, again, same thing, blue and the green here, and that blue never saturates on the discharge. So that was kind of what I was going for. So it looked good to me. Current sensor, which is implemented on the main board, which I haven't talked about yet. But so basically, okay, what's it for? It's load current, which is just going to whatever you're drawing off the battery. So whatever you hook up to the load terminals, input current from the solar panel, and so eventually, just calculate the V times I, power in and power out. So that's why I needed this here. Built the voltage divider here for inputting into the microboard, because this current sensor is, it ranges from 0.5 volts to 4.5 volts, and I can't put 4.5 volts into the microcontroller, so I built the voltage divider here for that purpose. And so this is my main board here. Here is that switching circuit, right? And the classic buck circuit configuration slide here going on. And I also have the blocking diode here, the 10 amp fuse I was talking about, current sensor here, and there's another capacitor here, sort of shown on the classic circuit page, but that's basically to help filter out the input, and as well as a 10 amp fuse going to the battery here, so from the battery, and the current sensor here measuring the load, and which I also I built this this here, which is very similar to this over here. Basically, that's the load on-off control. So I have this, this resistor here, which I made very high because I want to limit the excess waste current flowing there. So, and all I needed was just, you know, a negative respect voltage here to turn that on and allow the load to, you know, have juice. So for my voltage sense circuits, for measuring the voltage of the battery and solar, I have this voltage divider also required because, again, same reason it can't, you know, you can't put in 12 volts to the, you know, if your battery's reading 12 volts, it can't read 12 volts right into the input, so I just made a divider here. And I also made this transistor network here as to help eliminate waste as well, so that that way that wasn't always drawing current. Only when I want to read that value here at V0 will I turn E21 high, which will pull that down low and allow that to, this one here to turn on. And so the S plus, so this one's from, this is a representation of the solar panel voltage, and that'll pull down, or turn on, I should say, and I'll be able to read the voltage there. So that's also required for the power in and power out calculations. Go ahead. And so the 5-volt regulator, back on my system diagram page there, is this switching regulator right here. Some parameters up there. Very good efficiency, which is nice, better than a like a LM7805 or something. And this is the microboard that I'm using in my project, as most of us are. This is the little IC here. That's it right there, the MP1584. Alright, and this is the add-on board. So here's the voltage sensor, voltage sensors here and here, switching regulator here, and the LCD here, which I also kind of built, just added to this transistor, and this is pulled up to VCC so that I can turn the backlight on and off. And these are the headers going down to the microboard, LEDs over here, push buttons. These are the current sensor voltage dividers. And this ribbon cable, just a 16-pin header going to the other board, the main board that we saw earlier. Okay, so it probably would have been a little nicer maybe to have like a flow chart here, charging algorithm. But the method here is not too complicated. It's basically for full charge, which is the bulk, less than 13.5 volts, and at the battery, then we're going to just say turn on fully, have that MOSFET on completely, charge up the battery, you know, with all the current that it can possibly draw. Once it gets to PWM regulation here, number 2, or absorption, it's going to regulate the voltage and maintain it around 14.4 volts for the last 10 to 20% capacity of that battery. And then it's going to drop down to this float level, which a good 12-volt battery should be reading around 13.5 or something like that. Put 0.7, but it should be between 13.5 and 13.9 or so. Just keep that floating around that voltage, and it's just going to keep that, basically trickle charge it, maintain it, top it off, you know, just keep it there. And otherwise, we have the low voltage disconnect, as I was talking about earlier, which is set at 11 volts. And then once it sees that it's back up to 12.5 volts or above 12.5 volts, it'll allow the load to be turned back on, so you can possibly turn the load back on. So yeah, this is good stuff. You know, it harvests energy from the sun, clean power, helps combat those greenhouse gases, and it's useful for small off-grid applications. Go ahead. All right, and this is kind of a, okay, so I added some source code over there, but it's not visible, but I have yet to complete the coding for this, but this is kind of the hopes of a final project with an LCD screen. Mine doesn't look like that, but a few indicator lights and external terminal block to connect. So this is kind of what I have now. And issues. Well, I've run into a lot of issues. One of them, I would say though, a big issue in my project is there's no temperature sensing, and it's actually pretty crucial for batteries to have temperature sensing, which I didn't touch on too much, but basically mine's designed for lead acid, flooded lead acid, deep cycle batteries. And temperature is pretty important because as even a few degrees changes, the charging of it should change as well. So that's kind of an issue with mine. And I suppose that's, yeah, questions? From anyone?
So on that slide, what would it take to add that? Can you just buy a module, so like the current sense module, and throw it out there? Or?
Yeah, kind of. I think there's like things like, they just look like little transistors for temperature sensing. I don't think it would take too much. The hardest part about it would be, you know, the coding of it is, you know, but
Okay.
for me personally, but.
Well, we can certainly add that. There is a temperature sensor built into the micro, excuse me, which we talked about back in the micro class, but that would just measure the temperature of the microprocessor. So you would want whatever this thing is to be on a long lead, right, and attached to the battery.
Yeah, kind of like bring it out to that terminal block as well, and just kind of, yeah, bring a separate pair of wires or something over it and land on the.
Okay. So you're done with your circuit boards, right?
What's that? I'm sorry, what?
Are you done laying out it looks like you're done laying out the circuit boards, so.
Yeah.
But we could add something to one of those headers, right?
Yeah. Okay, go ahead.
For the solar panel, was it just a positive and ground? Two leads coming out of it?
Yeah.
Oh,
If you go back to like slide 6, on this labeled switching circuit.
Mm-hmm. This one? No.
No, keep going back. Before those.
Yep.
One more.
This one here?
Yes, sir. No, I guess it's that one. That one there. Okay.
This one here? Yeah.
All right.
Yes.
Can you explain what that voltage divider is doing again? You might have said it, or I might have missed it, but.
Okay,
it doesn't
yeah,
really
so,
say.
basically, you know, the solar panel coming in, can be, like I said, it's kind of designed for a 24 volt nominal solar panel, which has an open circuit voltage of, upwards of 45 volts. And so when that, gets pulled low here, I don't want this to see negative 40 volts, because the gate to source voltage here is only negative 25. So I just built this voltage divider here and actually, well, I wouldn't see that anyway because the battery's going to pull it down. So it was another number I calculated, and so that's why I got these two resistors to ensure that I would be on the safe side. voltage divider, just to,
Yeah, so it's really a protection mechanism for the transistor.
yeah.
Okay.
And when this gets turned off, I wanna, probably wondering why these aren't, higher values or something. This, they did require to be, like at least 3/4 watt resistors here, but the reason why I didn't go higher is because the gate charge here, when this goes off, has to discharge in order to fully turn that off. And so I kept this as low as I possibly could in order to keep that time constant quicker, make it faster, turning off.
Any other questions?